Okie dokie, earth science time. We're doing this in purple. We're going to do this in purple. So get out your purple. Today we're talking about the very, very wide world of plate tectonics. One of the reasons I say very, very wide world of plate tectonics is that they do cover the whole actual literal world. And another one is that we got a lot of stuff to talk about. I have a lot of stuff to talk about. I want you to help me. Plural. I want y'all to help me. First, I gotta roll my sleeves up so I don't get sweat everywhere. Gross. No, Peyton, not those. The like cardboard ones with the drawings on them. Okay. What is this? What is plate tectonics? What's special about this?
Plate tectonics are underneath us moving constantly.
Okay. Yeah. So they're things that we might say that the ground is made out of, right? It's Earth's whole surface broken up into segments. But not broken up into segments like the United States of America is broken into states, because those are imaginary. The tectonic plates are real, and they have real boundaries. But they do make up the whole of planet Earth. So these are segments.
States are not real.
Exactly right. States are not real, except for Hawaii. And nope. That's a false boundary. Yep. There are realer state boundaries than other. The eastern border of Nebraska is the Missouri River, and that's a real thing. The Missouri River do exist. It really do be that way. But most state boundaries are made up. Anyway, so segments of Earth's, let's put lithosphere. Let's put a verb in here. That do what? What do they do? Relative to? They move relative to, to the, what are they riding on? They are lithosphere, but they're riding on the what? Don't look at me like that, Lily.
Other sphere.
The asthenosphere and each other. Let's define lithosphere and asthenosphere. Let's do it like this. If I'm going to draw the Earth from the outside in, I was going to do the inside out. I'm going to do the outside in. Let me get my always prop that I use for this whenever I can, whenever I have one. Check it out. Check out what I got. Check out what I got, YouTube viewers. Got a stem in it. Look at this. Apple. Very good. You're really good at science. Earth. You see this red stuff on the outside? This is really gonna pick up on the mic. The mic is just gonna be like ASMR. It's ASMR. You see the red stuff? The red stuff for us, this is the skin, and that represents the crust. And it's about, the reason I like this example so much is that the evidence suggests that this is about the same ratio, skin to apple, as the thickness of the crust is to the whole of Earth. Okay? What would this white stuff, let me get another bite here.
This really is a mukbang. You like ate before.
What did you call it?
A mukbang.
Mukbang. This is where you watch someone eat on YouTube.
Yeah.
So this is my first mukbang. This is an apple from Walmart.
Did you get that
organic?
from TikTok shop?
No.
Have your fingers against the apple on the mic. Yeah,
I don't know. I'm embarrassed. Let me get this little piece of skin off there. Okay, so check it out. With approximately the same ratio as what we see here, we have the crust, the white stuff in the apple, what's called the flesh of the apple, so that's cute, is the mantle. Then there's this kind of like pithy area in the middle of here where the seeds are, called the core, but that to us is going to represent the outer core. And then in this apple, we might say the seeds themselves, or in our drawing, of course, we would have the inner core. Now, tell me what each of these things is like. What's the inner core like? What's it made out of, and what's special about it?
Made of iron, whatever word was in the book yesterday.
It's made of iron and nickel. And what state of matter is it?
It's liquid.
Let's try again.
It's solid.
It's solid. The inner core is solid, iron and nickel. Surrounding that is the outer core, made also mostly of iron and nickel, but it's a Liquid. Solid iron and nickel. The outer core is liquid. The mantle, what is that like?
It's kind of a mix.
It's not really a mix so much as it's kind of intermediate, I think is what you meant. Like it's neither liquid nor solid. It behaves on the large scale in a liquid manner. It does flow to some extent, but and we could put liquid, but that's why we use the word asthenosphere. The Greek word asthenos that this is based on means weak.
It's like slime.
Okay, so it actually is what we would call on this scale solid, but when taken as a whole, it is free to kind of fluidly move. It's maybe the consistency we might think of as peanut butter, but the mantle do flow, and that's going to be extremely important here. The mantle does flow, and the crust, of course, is solid. Now, be careful because the whole mantle doesn't flow. We have this other dividing line that I'm going to switch back to purple for. The mantle doesn't flow. The mantle is actually composed of the top mantle, which is more or less solid, and the inner mantle, which is more or less liquid, and that's where we get these. So this inner mantle is the asthenosphere, and then the lithosphere, to make matters a little bit more confusing, is actually both the crust and the top layer of the mantle. So the lithosphere is the crust plus the top solid mantle is the lithosphere. Lithos, where asthenos means weak, lithos means rock. So like the opposite of weak, like Dwayne "The Rock" Johnson, who is the opposite of asthenos, obviously. So we have these kind of two models for Earth's structure. Crust, mantle, core, and lithosphere, asthenosphere, core. Do you see the differences? I hope you do. How do we know? That's an excellent question for Earth scientists. How do we know? How has anybody been here?
No.
I mean, on planet Earth, yes, but you can't. We have never, to my knowledge, drilled into the asthenosphere. So no, we can't. How do we know? Okay, yeah, we can observe other planets, or even the formation of planets in other solar systems. That's a great. I didn't think about that one. That's good. What else? What's another piece of evidence? You should know from your we just make an assumption, making an ass out of you and me. That's what assume means. No, what else? How else do we know? Yes, exactly that. So the main evidence we have for this is seismic waves. And we're going to make a little side note over here, a seismic side note. We're going to talk about earthquakes real quick here. As you know, Earth is made out of segments called plates. And these plates, the boundaries between them and within them are faults. Faults are just what we call any crack in Earth material. They can be large or small, but any crack is called a fault. Rocks that we can see, for instance, of the buttes might have faults. In this place, where we live is not really very tectonically active, but we do still see faults. There can be faulting because of weathering, but we're talking here about faulting due to plate tectonics. But these faults are cracks in Earth material. And along these faults, very frequently, once again not here, but very frequently, things move. I have my fault blocks here. So you can see this crack between them is a fault. Yeah? You with me so far? And the movement along this fault could result in an earthquake. These if they're free to move past each other, they can move in several different ways. And we'll talk about the plate boundaries here in a second also. But for the faults, we have this crack, the fault on the top. And if I am pushing them together, let me make sure I get this right, because one of them, this is something I do very frequently get wrong. So hold on a second. I want to make sure that I get the direction of the faults right. Does anyone remember from their reading off the top of their head which one is a normal fault and which one's a reverse? I don't want to get it wrong. who has their Chromebook out? Would you look it up real quick? Tell me which one is what I'm looking for, Peyton, is I know one of these, when they come together, it goes like this, and the upper one moves more up. And that's either normal or reverse. And when they move apart, the upper one kind of is free to fall down. And I think that's the reverse one, but look up for me which one it is.
What do you mean like with faults?
Just type in normal fault. Okay, good. So in a normal fault, these are moving away from each other, and this one's kind of free. You see, if I pull them apart, I'm trying to put very little pressure on them. If you pull them apart, this one's free to slip down. That's called a normal fault. Let's diagram it. I mean, I did just kind of do that, but I'm going to do the exact same thing over here. So the force is pulling them apart. They are diverging, and that causes a normal fault. In the reverse, these, if they were a little bit slipperier, it'd be easier. But if I push them together, you can see they the one that is upper keeps moving more upper. That's called a reverse fault. They're being pushed together, and so the one that was up, this is now called a reverse fault. And this might happen at a convergent. Do these two words make sense to you? Converging and diverging? Remember, the prefix con means together. They're coming together. The prefix di means, well, separate or two, but they're moving apart from each other. So when these two things, whether they're plates or just pieces of rock, diverge, they're free to fall apart, and that is a normal fault. When they converge, they're pushed together, and that's a reverse fault. You with me so far? There's a third type, which I do remember, and that is when they move laterally past each other. So now this one, we're going to look at it in map view. Map view. Remember, that's from the top. These are moving past each other laterally, and this is called a strike-slip fault. And this is a transform plate boundary. If it does happen at a plate boundary, it's a transform plate boundary. So that is this. Because remember, things are three-dimensional, so they can move in this way too. Yeah? Transform. Trans meaning across, form meaning shape. Okay, so normal, reverse, transform. Divergent, I did convergent. Convergent when they come together, transform. Yes? So those are the plate boundaries and the way they can behave at faults. Now, when these things move, there's a certain amount. It's almost kind of like when you stretch a rubber band and eventually it snaps, because the force that's acting on these is always acting on them. So how come they only move once in a while? And what do we call it when they move? It's an earthquake when they move. But why do that only happen? Why, if the force is always acting on them, why is it not just like, and we just always have a low rumble? It moves really fast when well, maybe not really fast, but it's on average, it does move really slowly, on average. But it doesn't move like this. It's not nice and gentle, because there's an enormous amount of force on them. It moves like that. Like there's a sudden jerk. Like there's always force on them. It's just that sometimes, like a rubber band snapping, sometimes they move kind of all at once. And not usually this much. Like that would be crazy. If this were like a river on there, it's like, whoa, and then there's a 3 mile. No, probably not. But it does, like the moves, even you can see it's not very smooth there. If you put enough force on it. Though a lab we used to do in 8th grade science was that you would take a book and put sandpaper on it, and put sandpaper on the table. So you have these two sandpapers touching, and you pull on it with a rubber band, and you would notice that even though you're putting a constant force on it, it moves all of a sudden at once. And that's the idea of the earthquake. What should I write down for that? So the earthquakes happen due to, Yeah, actually, you know what? That is not a terrible example because there's this idea of a stress-strain curve where I'll just graph it here and then I'm going to erase this pretty fast. But there's a certain amount of, if we put, let's put force on this axis and deformation on this axis. So for a while, we get this kind of constant force, and then it kind of drops off because the force, once this deformation does occur, the force, and this is where we get the strain, where these things suddenly move past each other. So the force is fairly constant, and then they move, and the force is alleviated momentarily, or not the force is alleviated, but the deformation is alleviated momentarily, and there's a big motion, there's a big deformation. And like Kyler said, it's kind of like when you get slowly in your life fed up with the way things are going, like this goes wrong and this goes wrong, and none of it's very big, but that happens 100 times and then you have a mental breakdown. And that's an earthquake. It's like a physical breakdown. Yay! Yay, Earth. What causes there to be a force on these things, though? Nope. I mean, it's not completely unrelated to gravity, but it's not primarily gravity. What causes there to be a force on these, on the plate tectonics? What causes them to move? Yeah, exactly right. It's heat. So we're going to take a little segment of this. I took the wrong segment. We're going to turn it over. Down here is the what? Core. And what's true of the core? What's it feel like down there? Hot. 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 Where's it hot at? Yeah, it's hotter near the bottom. Remember the old science fact that you've probably heard before, that the core of Earth is hotter than the surface of the sun. And it is. It's very hot. It's hotter down there. What's true up here?
Not hot.
Yeah, cool. It's cool. This is where you live, and so therefore it's cool. It's where all the cool cats live, actually, and also the regular cats and the idiots. Everyone lives up here where it's nice and cool, because this down here would be too hot for us. And just like... What? And now I've just offended them. Like, they have access to YouTube, but they never post on YouTube, and the mole people are like, how dare he say we're uncool? Yeah, that is what I'm worried about. But this is kind of like a pot of water boiling on a stove. This is all... Wait, what's up here?
Crust.
Let's call it lithosphere, but sure. And that means all this stuff is asthenosphere. So kind of like water boiling on a stove, when it gets hot down here, or my lava lamp is a great example, when it gets hot down here, it gets lower in density, and it moves to the top. And then when it's up here, it gets cold again, and it gains density, and it goes to the bottom. And we have these cycles, and that ends up being, if there's two of these currents next to each other, we get this break between the lithosphere up here that might cause, in this case, it would be a, well, I want to draw this, I want to pretend this was drawn the other way. It will be a fault, yep. I'm going to draw this one the other direction. Wait, it can't be going both up and down. That doesn't make any sense. There we go. There we go. So this one would be, if this one's moving clockwise and this one's moving anti-clockwise, or in America we say counterclockwise, this fault would be divergent, which would lead to faults like a normal fault, for instance. Yeah? A divergent plate boundary. What kind of things can happen at divergent plate boundaries? Remind yourself that there are two kinds of crust. Remind yourself that there are broadly speaking, two kinds of crust. Two kinds of crust. What are they? Nope. They're all crust is the lithosphere. Good.
Crust on Earth and the crust on your bread.
No. What kind of crusts are there, broadly speaking?
Earth's crust.
Okay, I'll accept it. I don't like it, but I'll accept it. Oceanic is one. Oceanic. And what's the other then? This is what I thought you meant when you said Earth's crust, but I now realize that you were not knowing the right answer. Continental. Let's list some attributes of these. Oceanic is what? What kind of rock largely?
Basalt.
Basalt, very good. Basalt, high or low density?
High.
High density, which is indicated with the Greek letter rho. Continental then is mostly granite, or it's largely granite. And which with relatively low rho, low density. So if we have this divergent plate boundary here, it could be either continental, it could be oceanic, continental, or it could be oceanic, oceanic. I don't know why I abbreviated continental but not oceanic, but I did. If we have a continental divergent boundary, we call this a rift valley. The land is separating from itself. This is currently happening in southeastern United States of America, somewhere. It's called the New Madrid Fault, and it's somewhere in Mississippi-ish. I think it's happening in eastern Africa, in the East African Rift Valley. But basically, a new plate boundary sometimes is forming, and the continent itself is splitting. A rift valley. What if it's oceanic continental?
It forms a. It's not
A lake.
Wild guess, unhinged guess. But no, not probably. Maybe. I mean, I'm sure somewhere along there it would. Yeah, probably form a lake. But this is kind of like, in some places we see this in the Ring of Fire, and it is sometimes associated with volcanism, but not as much as another thing that we'll talk about when we do convergent. What about oceanic?
It forms a.
This is like what's happening in the middle of the Atlantic Ocean.
It's like the big thing that falls inward in the ridge.
Mid-ocean ridge. Mid-ocean ridge, yeah. It actually, as it separates, I'm going to use these, even though these are supposed to represent continental crust. Stay here, please, Marco. If this is the oceanic crust on the bottom of the Atlantic Ocean, as they separate, why would they separate? Because someone's out here pulling on them? No, what is the force that my hands are representing? No. What do we call this process? Convection. She actually knew it. She just was giving you guys a chance. Convection. I should have said that earlier too. But the convection is what is providing. So my hands here are representing convection. Oh, they got my tie. My hands here are representing convection. And the oceanic crust is separating. And as it separates, it just empty space. No, what's pouring up through this widening crack? A little bit. What? What's down here?
Oh.
What's coming up?
The hotness.
The hotness, the asthenosphere. Right, there's stuff down here. So as this separates, gosh dang, well, this will work, I guess. Asthenosphere comes up. Mantle comes up through it and solidifies, and actually it kind of pours up. No! The earth! It kind of pours up. I'm going to try to separate this with one hand. There we go. It kind of pours up out of here. And up here forms a mountain range called a mid-ocean ridge. On the continental crust, that usually doesn't happen. Usually that just kind of separates like that, cracks open, and we end up with this rift valley here, where a lake often is. There is often a lake here. So if lake is what you're thinking of, lake is what you're going to get here. That's for a divergent plate boundary. Now, let's reverse the flow of one of these. Let's actually reverse the flow of both of them. Let's say that this convection current, which is what we call these, by the way, this convection current, where'd my marker go? This convection current, erase. Has everyone got the different divergent results here? Oh, and by the way, can an earthquake happen at any of these?
Yeah.
Sure, anytime there's plate motion, an earthquake can happen.
Isn't that how a tsunami starts?
Yeah, it can be, yeah. If there's an earthquake in the deep sea, it'll generate a big wave like a tsunami, yeah. Let's reverse these currents, and now we're going to have them. Wow, dang it, man, I am really bad at knowing what to do. That was right, actually, so I'm going to redraw that. And then this one I want to go like this. There, two more convection currents. These ones are pushing these together. It's not divergent anymore, it's called
Convergent.
convergent. Let's do it again. If we've got two continental crusts colliding, if we've got an oceanic continental, and if we've got two oceanic. These are going to be our examples. What about if it's two continents colliding? Like, for instance, if it were two wet little graham crackers being smooshed together, what would happen? Mountain. What we call a crumple zone mountains. Crumple mountains. Crumple zone mountains. I'm going to abbreviate mountains as MTS. And it's just like if you take two pieces of paper and smoosh them together and they kind of like, come on, smoosh together. Not a very good example. Look at like that. Mountains. Ta-da. Ta-da, mountains. Okay, so it is stupid, but does that make sense? Do you see how that would be that way? It really do be that way? Okay. Another thing that can happen, and that's because these are both relatively low density. With this one, one of these noticeably has a larger density. The oceanic crust is more dense, and therefore it subducts. Oops, I wanted to use my pink again. Subduction. Subduction zone. And that's like this. This guy's more dense. How can I represent that?
Oh, is it the Humboldt and the Graham?
Let's get this guy. This guy's more dense.
It's gonna go.
Okay, maybe not quite that sharply, but something like that. Yeah, does that? So this one's more dense, and so you can see it's just really hanging out there. This is the continental crust. Yeah, less dense. This is the oceanic crust, more dense. The foam, aka foam bowl. Yeah, and so at this, I wish this would stay up, but I need one more hand. I'm going to use my nose. Right down here, like it's getting down here, you see? And it's getting hot. Remember? Hot. And that subducted plate is going to start melting. Uh-oh, melting right where my nose is. And it's going to get less dense, and it's going to go all the way up here. And it's going to cause a mountain range to erupt right here, a volcanic mountain range to erupt right up from where the subduction zone is. So we're going to end up with this mountain range. Origami. I'm going to get this to look really good. There we go. Like that. That's what we end up with because this mountain range forms here because of the molten material coming up. And that's where we get a lot of volcanoes. Featuring volcanoes. Still some earthquakes. The same thing can happen. No, don't. That's not a funny joke. The same thing can happen with oceanic. It can also subduction zone. And it can also feature volcanoes. Speaking of volcanoes, that's going to be our next thing. Speaking of volcanoes, they vary depending on the type of crust that has been melted. So we're moving on now to regarding plate tectonics, but now we're moving on to volcanism. Which we call extrusive igneous activity. I'm trying to think of where would be the best place for me to write. I'll do it over here. Is that okay? Yeah. Is that okay was a rhetorical question. I already know it's okay. I'm doing it. Okay. I'd like to erase this too. Can anyone hurry up and write this down? You have these different products of these convergent plates. We've kind of stopped talking about transform, but that's where most of the earthquakes happen is at transform boundaries because of the stresses that are pushing it along it this way. And usually transform plate boundaries are associated on a larger scale with either convergent or divergent, but you'll end up with something like from the sky that would look kind of like this. So like altogether, these two plates are diverging, for instance, but right here is a transform plate boundary. Do you see that? So that we usually have these smaller transform plate boundaries along a larger diverging boundary, for instance. Oh, I was going to erase. Extrusive igneous activity, also called vulcanism. Extrusive, why? Igneous, why? Activity. Why? Why extrusive igneous activity? What's extrusive mean? Yeah, coming out of. What's igneous mean? That it's those rocks that are formed from. No, not only. No. Yeah, what do we call the molten rock? Magma. So it's outside Earth or on Earth's surface, outside from magma, and then you know what the word activity means, I think. And we call these rocks, as we talked about during the igneous rocks part of our rock cycle video, we call these rocks volcanic if they form outside of Earth. And what's a characteristic of volcanic rocks? How can we look at an igneous rock and say that's volcanic as opposed to intrusive or plutonic? What is true of the extrusive igneous rocks? They cool more quickly or slowly? Quickly, because they're on the surface, and therefore their crystals are smaller. They're smaller crystals because they cooled outside of Earth. And usually from something like volcanoes or other kind of what we call volcanic activity. And these can be of several different kinds depending on what kind of crust, not the kind of crust they are happening on, but the kind of crust that the magma is made from. So for instance, let's do two different examples here. Let's have a subduction zone, continental crust, right? Oceanic crust. And then over here we'll have a crumple zone. Okay. Oops, sorry. Let me continue that. Continental. With me? First of all, where will a volcano form here? Cool, thanks. So it's going to, as I said, melt down here. This will be a little bit better in case you're a visual learner and not someone who learns by papers flopping around in outer space. But as that crust melts, it forms this conduit here, and this will be a volcano. And this volcano will be made of what kind of magma? What kind of magma will come out of the volcano here? Okay, molten, very good. But it was oceanic crust that had melted, and so what kind of volcano will this be? Basalt. Basaltic magma. And that produces what we call a shield volcano. It's called a shield volcano. I spelled it Shyled. I'm going to leave it, but you should spell shield right in yours. A shield volcano because it's kind of wide and flat. Because another thing about oceanic crust, high density basalt, but it is runny magma. The magma is runny. The kind of the way we think about it is it's kind of like honey, runny honey. It's viscous. It's more viscous than water, but it will still, even if I had some honey right here, which I actually do in my desk, but I've already made a mess on the floor once today. But if I had some honey and I poured it out, it would kind of, it'd puddle out. It's more liquidy, and that forms a shield volcano, which is usually pretty broad and flat. A shield volcano. The Hawaiian Islands are made of basaltic magma. They form broad, flat volcanoes. Interestingly, as a side note, the Hawaiian Islands are not formed at a subduction zone. They're at a hot spot, which is just when this kind of happens, like there could be a minor convection current right here forming a hot spot, and that just forms this little volcano right here, and that's Hawaii. Oh, not high. Aloha. And that can form at a hot spot. Aloha. Hot spot. I assume the way you say hot spot in Hawaiian is Pele, because remember that's the volcano god. But so there's Hawaii and how it formed, just as a little sign note. But it is basaltic magma, because it's still happening in the oceanic crust, and it forms a shield volcano. Now this one will be, I'm going to do this in blue, I guess. Granitic magma. How do I know? Because both of these are continental crust, right? So they're granitic. And so it's granitic magma. And whereas basaltic magma was runny, granitic magma we say is chonky. Well, we say chunky, but I say chonky. Chunky magma. This is more like, if I was going to pour it out on the floor here, like a blob of peanut butter. Right? It would not spread out. Maybe over time it would slowly spread out. But the thing about this is that this granitic magma, because it's chonky, and actually has quite a lot of gaseous water vapor or other gases in it. When it comes out, instead of, you think about, and they did this one time in one of our How the Earth Was Made videos, they take two beakers, one of, I think, honey, or something like it, and one of peanut butter. and they heat them both up. And then one of the honey gets hotter and it starts to boil, and it's kind of gently like a rolling boil, like water almost. The peanut butter one, you can imagine, is like it keeps having these big explosions, because the higher the viscosity, the more it's going to explosively heat up. So the granitic magma comes up through this conduit, kind of like the basaltic magma did, but instead of nice, runny, smoothly flowing lava, it is an explosion. Like Mount St. Helens. And that generates what's sometimes called a pyroclastic flow.
Which happens to the people of Pompeii.
Exactly right, Pompeii. That's how most of the people in Pompeii died, because it was a granitic eruption. And so there's even a question on your test that is, how did most of the people in Pompeii die? And one of the choices is they were burnt up by lava. They were usually encapsulated by the pyroclastic flow. Yes, yes.
Hotspot in Hawaii is
Pico Pile. I was pretty close though, because I said Pele. That's really good. Thank you. Thank you. Aloha. How do you say thank you? Mahalo? Or is that family? What means family? Ohana means family. So mahalo is thank you. Mahalo for telling me the hotspot is Pico Pele. Very good. I wonder what Pico actually literally means, because Pele I know is the volcano. No, Pele means volcanic, right?
So Pico is probably like spot.
Spot, just place. Sure, I'll go with it. Do you see the differences between? Oh, and by the way, this kind of volcano that forms from it is usually called a cinder cone or a composite, and it's formed from, as it erupts, it forms from layered ash.
The navel where life begins.
That's beautiful. Pico Pele, the navel where life begins of Pele, is the hotspot. And that's true, because for the Hawaiian Islands, that is very accurate. That is indeed true. Somehow I think all of this was a side note, because we were talking about initially, how do we know that Earth's crust and the interior is this way? Because we were talking about seismic, and that was hours ago, right? How long do we have? 0. Now listen to me. We did not have time to talk about plutonic activity or the actual mechanisms of earthquakes. So I'm going to... No, we'll talk about this tomorrow. We will continue the discussion tomorrow, but we will not move the assignment to Thursday. We'll do the discussion tomorrow. We'll continue the discussion tomorrow, and then we'll go over the assignment. I think there'll be plenty of time for that.